Good morning, good afternoon, good evening, depending on where you are. Welcome to the OPAL-RT learning journey. Today we have a very interesting talk on innovative software in the loop testing for grid forming converter control. First, let me introduce myself. My name is Etienne Leduc from OPAL-RT. I'm the offering manager for the energy market, and I'll be responsible for hosting this presentation today. Sakib, if you just want to go to the next slide for the introduction. Thanks. So I'm joined today by Nasmus Sakib Khan Shabir, who's electrical modeling and simulation specialist. He'll be the main presenter and demo operator for today's presentation. And we're also accompanied by Juan Felipe Patoroyo Montenegro, who also worked a lot on this project and will be able to help answering questions at the end. Feel free at any moment to start sending your questions through the Q&A menu that you have at the bottom of the screen, and we'll be able to answer them at the end of the presentation. So without further ado, I'll let Sakib start presenting.
Thank you, Etienne. This is Mohammad Nazrul Sakib Khan. I'm a electrical modeling and simulation specialist from OPAL-RT. Today, me along with Juan will be conducting this webinar. So before I jump into grid forming converter, is actually this grid forming inverter is a part of smart inverter library available in RTMS. So this smart inverter library is a MATLAB simulating based control protection system. This particular library was developed according to IEEE 1547 2018 standard. Within this current release of this smart inverter library, only grid following converter strategies has been added so far. This is the functions and the blocks you can see that is currently available in the smart inverter library. It contains some current control loops. It has some power controllers, and according to IEEE 1547, it also some protection for, functions that covers the frequency protections, that covers the voltage protection, current protection whenever there is abnormal situations. In addition, it also covers some configurable grid support functions that requires by the IEEE 1547 to support the voltage and reactive power control. It has constant power factor control. It has constant active power control. It has volt var control. It has volt watt control. In addition to support the active power generation control, it also been integrated the frequency watt control. In the future release, we are about to integrate this grid forming converter in the smart inverter library. Here it's worth mentioning that the smart inverter library was jointly developed with CanMed Energy Environments, and Natural Resource Canada owns all the intellectual property for the smart inverter library and its related products. So the first question will be asked, why actually we need this smart inverter library? So if we go back to past, our power generation was used to be mostly dominated by rotating machinery driven power generation units. And if we go to different simulation platforms available for power simulation analysis, there is an enriched library of different protections and control blocks for this rotating generation units. But in recent years, there is an increased penetration of renewable sources into our grid. And these renewable generation units are mostly integrated with the grid through inverter interface system. And if we look into this simulation platform for power system analysis, there is a lackings of proper toolboxes for this inverter-driven systems. To meet these lackings, we actually are working on to develop a smart inverter library so that the user can easily analyze different inverter interface system. In addition, the controller for this inverter interface system are pretty big in size. For example, if you look into this picture, this is a particular control loop for grid following converter, where we require some grid synchronization loops, where we require some power control loops to control the dispatch of power. We also need some current loops for inner synchronization. And at the end, beginning, based on the synchronization, the control loops required to generate some control signal that will control the switching of the inverter. And developing these control blocks from scratches is a time-consuming process, and it also requires some technical expertise to develop it. And to reduce the hassle from developing this controller from the scratches, we have been developing this smart inverter library so that user have the flexibility to choose like whatever the control loops they want to use in their control system. In addition, since the beginning, that this inverter interface system has been integrated with the loop with our power grid, so many challenges have been faced so far, and to address these challenges, many advanced control algorithm has been developed. Many grid system has already implemented many grid codes. There are so many standards, like over here, IEEE 1547 has some standard for distribution system level generation units. IEEE 2800 has some standards for transmission level integrated inverter interface systems. So there is a lackings of all these advanced control systems, all these protection standards in a centralized way. So our object is over here that so that we can have a enriched collections of all these advanced controller, all these like protection functions. And the good things over here that all these controller and all these protection functions, particularly this whole toolbox has been developed in a modular way, so that it remains scalable and it can be flexible, so that whether which advanced functions the user needs to use, they can select it easily. They can use it in different ratings of the inverter, in different levels of the power distribution system, and also like depending on the requirement of the system, they can use different blocks that is available in the smart inverter library. In addition, the protection functions that's been integrated in the smart inverter library, they're actually configurable, so that although it was particularly developed for IEEE 1547s, but based on this configuration, like the configurable characteristics, these blocks can be applied in any grid standards. User can modify them depending on their need. And most importantly, all these toolboxes has been developed so to reduce the computational burden, so that we can easily implement them in real-time simulations. So currently, if we broadly categorize these inverter control systems, we actually can categorize them as a grid following, or it can be grid forming. So if we consider a distribution system where we have some generation units connected over here, and we also some load that has been connected with this distribution system. And this distribution system can be connected with the grid. And if this is the case, when a distribution system having some load and generation units connected with it, and this particular system is connected with the grid, then usually this generation units doesn't regulate the voltage or frequency of the system. Grid itself regulates the voltage and frequency of the system. This generation units merely follow the grid. And that is the case, this control algorithm for the inverter interface system, we address them as a grid following converter, because they're merely just following the grid. But if a situation arises where this grid suddenly got disconnected, and then these whole distribution systems become islanded. And in that case, these generation units available into this distribution system have to take charge to form a grid, so that the voltage and the frequency can be maintained by dispatching the required active and the reactive power. So in that case, we address them as a grid forming inverter. So with the current release of the smart inverter library, the grid following inverter has already been integrated. So whenever a user wants to do a study on a power system that is connected with the power grid, they are welcome to use this grid following inverter. With the next release, the grid forming inverter, when there is no grid connected with the system, in that case, we need to use this grid forming inverter, which will be integrated in the future release of the smart inverter library. So, and this Usually, this grid forming or grid falling, so whatever we address them, so this control algorithm usually developed in layers. So it can have the tertiary controller, it can have the secondary controller, it can have the local primary controllers, and it also can have like to protect the equipments of the system and to protect the equipment of the generation units. It also requires some protective relays so that whenever there is abnormal situations that goes beyond the capacity of the equipment, that protective relay can kick in and saves the system from being further damaged. So giving all these minds, all these functions for primary to secondary to tertiary, all these control blocks has been developed into layers so that if user wants to whatever the control algorithm, whatever the control layers that the user needs to use, they just can pick and choose them and put them into their simulation model and do their analysis. Okay, so with this current with the grid forming converter, it actually offers 4 functional blocks. We have the signal conditioning blocks that actually conditions the signals according to the requirement of the subsequent blocks. We have an outer control loop where the grid forming control algorithms are present. We have the inner control loops that actually do the synchronization purpose, and we have the reference generation blocks that will conditions the control signal according to the settings, according to the nominal setting of the inverter that is controlling. So if I need to give a brief description of the control blocks, in the higher level, we have the signal conditioning blocks. All these control blocks has been developed so that it operates in per unit, and it also operates in DQ coordinate. So the function of the signal condition blocks that the voltage and current measurement conducted in different parts of the system, it conditions them into per unit system and convert them into DQ coordinate signals so that the subsequent signals can be benefited from it. While this is the graphical representation of the signal condition blocks. So if when choosing user request to some of the nominal settings like the voltage, the DC voltage settings, and the nominal powers, and based on these settings, these signal conditioning blocks will condition the signals and convert them according to the requirement of the subsequent blocks. Then in the second level, we have the outer control loop. The main objective of this outer control loop to provide some set points for the inner control loop, and it also aims satisfying certain system level specifications. That these system level specifications can be maintaining the voltage and frequency of the system, ensuring proportional power sharing among the distributed generation systems connected over with them. So this sort of objectives are usually made by the outer control loop, and outer control loop ensures that all the reference required by the inner control loop will be generated by the outer control loop. So this is the graphical representation of the outer control loop. So while choosing user usually required to choose which particular outer control loop they need to use. With the current version, we have the Droop control, we have the virtual synchronous generator control, and we have the sync converter control already provided with the outer control loop. So depending on the choice, different parameters are required to put over there. Like for Droop control, user just merely need to provide the Droop coefficients. For the virtual synchronous generator control, they need to provide some inertia characteristics. Here, it's worth mentioning that both all these control algorithm like Droop, VSG, or sync converter, they mimics the characteristics of the synchronous generator. If you ask me the fundamental difference, the Droop control mimics the steady state characteristics of the synchronous generator, whereas virtual synchronous generator mimics the steady state and the transient characteristics of the synchronous generator. For the sync converter, it also mimics the steady state and the transient characteristics with added impedance with it. And for this reason, the sync converter doesn't require any inner synchronizations. So that's why when choosing the For the Droop control and the virtual synchronous generator control is usually provides a set points for the inner synchronization units. But when choosing the sync converter, it directly generates the control signal. Because of that added inner impedance with the sync converter, it doesn't require any inner synchronizations unit. Then in the next control loop, it will be the inner control loop, and the main objective of this inner control loop is to execute the reference that was set by the outer control loop. It also performs the inner synchronizations. So with these current versions, in the inner control loop, we have a multi-loop control and we have a single loop control. So in the multi-loop control, we have both a voltage and current loop control for the inner synchronization, whereas in the single control loop, we only have the voltage control loop. As in the single control loop, we do not have any current control loop. Due to the absence of this current control loop, this single control loop is susceptible to flow of higher current during larger disturbance. As a safeguard, we have introduced virtual impedance with the single control loop, so that whenever there is a situation of higher current flowing through the circuit, this virtual impedance can act as a safeguard to protect the equipment it is connected with. Whereas in the multi-control loop, we use current saturation technique to actually curb the current to its maximum limit. So if when the user choose this single inner control loop, so first user needs to choose whether they want to choose the single control loop or the current control loop. So depending on their selections, they need to provide different parameters so that the blocks can execute properly. And in the innermost control blocks is the reference generation blocks. The main duty this this reference generation blocks perform is that the control signal that was generated by the inner control loop, it was generated. This control signal was generated in DQ coordinate. The purpose of this reference generation block, so that this DQ coordinate signal will be converted into ABC signal, and then that turns into the control signal. Then this control signal can pass to an PWM generator, and that PWM generator will generate the control signal, and that will control the switching of the inverter. So in addition to this, in some cases, users, to reduce the computational burden, sometimes users put a higher sample time for the blocks in comparison to simulation blocks to reduce the computational burden. And in practice, it introduces some phase angle error into the simulations. This reference generation blocks have added protections, so that if the sample time in the blocks and the simulation is different, that phase difference is automatically corrected. But here it's worth mentioning that while we're using these blocks in real-time simulations, all the sample time for these blocks and the simulation has to be the same. This is only helpful when we are doing our simulation in offline, just to reduce the simulation computational burden. So that's actually a brief descriptions of the blocks available in the Smart Inverter library. This time I will jump into a demo, so that the functionalities that actually I mentioned so far, I can show a demo and do a practical demonstration. So for the demo, I'll be using a island in microgrid. So before I jump into this demo, let me explain the islanded microgrid software. So in this islanded microgrid, we'll have two distributed generation units connected in parallel, and some loads also connected with the distribution generation units at the point of interconnections. The objective is over here that we at different times, like over here at 1.5 seconds, a 5 kilowatt 5 kVAr load will be connected at the point of interconnection, and which will disconnect it with the system from at 3 seconds. The object is over here with these varying dynamics depending on the choice of our outer control loop. Is this outer control loop is able to form a grid and maintain the voltage and the frequency within around the nominal value and meet the power demand. So that is the things that will validate it. And we also try to show that how easy this this grid forming inverter available in smart inverter library to use. Uh, Let me share my this is the example models that I was talking about. So if I go inside this load, you can see we have a static load that will be always be connected with the system. The connection of the and disconnection of the additional loads that will be controlled through a three-phase circuit breaker. If we go inside this distributed generation system, so we have a dispatchable dispatchable DG units connected with the growth through a two-level three-phase inverter. Here, this two-level three-phase inverter has been modeled as an average model, so that it doesn't we do not need to input a PWM signal over here. The ABC signal that is generated by the reference signal that will be directly fed into the UREF, and that itself will do the switching. And we can see that all of our control blocks that I have explained so far has been used over here. At the beginning, we have this signal conditioning box that is converting the current measured in different portion of the system and output voltage of the system and the DC measurement of the system. So all these are the input of this signal conditioning blocks, and we have selected different nominal setting for this inverter, and based on this nominal settings, the signal conditioning blocks is converting and conditioning the signals according to the requirement of the subsequent blocks. In the outer control loop, we need to choose whether we need to use the Droop control, we need to use the VG control or the sync converter. And this outer control loop will generate some reference voltage. It will generate the angular frequency and phase angle for the system. And in the inner control loop, we have the choice to use whether we want to use the double loop control or whether we want to use the single loop control. And finally, this inner loop control will generate the final the control signal in DQ coordinate, and the reference generation unit that will condition these signals according to the settings of the inverter, and it will convert this control signal from DQ reference to ABC signal. So this demonstration, I actually organize them in a two separate way. In the first demonstration, both of these two DG will have the same ratings, and the rating will be 5 kilowatt. And for these similar ratings, we will use the efficiency of the Droop control. We also will see the efficiency of the VSG control. Then in the next round, we'll use DGs having two separate nameplate capacity. So in that case, the capacity of DG2 will be twice of that of the DG1. And in that case, DG1 will have a 5 kilowatt nominal capacity, and DG2 will have a 10 kilowatt of nominal capacity. So before let's jump in. And right now, both DGs have the similar 5 kilowatt capacity. And in the inner control loop, we have used double control loop that incorporates both voltage and current control loop. And in the outer control loop, for the first demonstration, we are about to select Droop control. And let's go to DG2 just to see. Yes, our outer control loop is Droop control, and our inner control loop is double loop control, as it was set in the DG1. So if we run this simulation model, so what we expect that the both DG will share the same amount of active and reactive power, and the voltage and the frequency will be around the nominal value. Here we can see the figures on the right, that we have two DGs. The first, on the left graph showing the active power dispatch, the right graph showing the reactive power dispatch from the two DGs. And as both DGs have the same ratings, they're dispatching the same amount of active and reactive power. And here you can see that our voltage and frequency remains around the nominal value. It's very close to 60, but that is one of the limitation of the Droop control, that unless additional secondary controller blocks or other blocks has been integrated, it tends to deviate from the nominal value. Here you can see that like right now it's around 59.1, and when the additional load being connected, it further drops, and when this load got disconnected, the frequency improves again. Then in the second demonstration, I want to show that if we choose instead of Droop control, if we go for the VHG control, how the system respond. Here, I'm also trying to show that how easy we can study different control algorithms with the smart inverter library. We just need to select the just different control algorithms available in our toolbox, and then based on our settings, the system will run, and we can do our analysis for stability analysis or how the controls are performing. So this is the demonstration for the VHG control. Here you can see that as the both DGs have the same capacity, both DGs still sharing the same amount of active and reactive power. But instead, as it was promised that VHG will improve the frequency, here you can see that earlier it was something around 59, but with the VHG control, the frequency is significantly improved over here. And here it's worth mentioning that when this VHG control or Droop control, it actually controlling the active power generation. For reactive power generation, in both cases, we are using Droop control, and that's why the voltage generation characteristics remains the same for VHG and the Droop control. So this was the demonstration of the smart inverter library for VHG control and Droop control when we have the similar capacity. So in the next example, instead of similar capacity, we'll use different capacities of DGs. So in this case, our DG1 will have 5 kilowatt capacity, and our DG2 will have 10 kilowatt capacity. And for the first demonstration, we are going to use Droop control here as our outer control loop in both DGs. So we can expect that with this version, again, our voltage and frequency will remain around the nominal value. But in this case, our DG2 should have dispatched twice that of the DG1, as DG2 has double capacity of that of the DG1. If we run it, so here, so here you can see that. So the red one, this is the active power dispatched from the DG2, and the black one, this is the active power dispatched from the DG1. As DG2 has double capacity of that of DG1, DG2 is actually contributing more active and reactive power based on their nominal settings. And again, you can see that, the voltage and frequency remains very close to their nominal value, as it was expected. So in the next demonstration, we'll change our outer control loop from Droop to VHG, and let's see how this control algorithm works when our DGs have different nominal capacity. Again, well, we can expect we have two DGs with two different nominal capacity. That this power dispatch should be according to the ratio of the nominal capacity ratings. Again, even for VHG, the two control algorithms for the DG2 is dispatching twice that of the DG1 for both active and reactive power. And according to the characteristics of the virtual synchronous generator, the frequency profile is significantly improved in comparison to that of the Droop control. So this wraps up the demonstration of the two control algorithm. In the next control algorithm, in the next demonstration, I would like to see a comparison in between Droop and VHG for the same settings. To make a fair comparison, so in between Droop and VHG, here we're using two distributed generation system connected with a load, but they are not internally connected. They're completely separated connection system. The line parameters and loadings for both cases are basically the same, but only difference over here is for the DG1, it is driven by Droop control. And inner control loop remains the same for both DGs. It's double loop control. And on the DG2, our outer control loop is VHG. So we want to see that how this two control algorithm performs when we have the similar settings. So what we can expect that the both DGs, as they have the similar settings and similar capacity, their power generation, that the power dispatch should be the same. But as DG has some inertia characteristics, its frequency profile should be better than that of the Droop. Here we can see that for the VHG, frequency is significantly better than that of the Droop, and it's very close to the nominal value. It's not exactly nominal value because of the absence of the secondary controller. And with the VHG, it has some, due to its inertia characteristics, it takes some time to get to its final value. Whereas in Droop control, due to the absence of inertial characteristics, whenever there is a reference change, whenever there is a change in dynamics, it instantly changes power dispatch. And that's the reason usually Droop control lacks the inertia into the system it is connected with. That's technically wraps up the software in the loop demonstration of the grid forming converter. The application that I showed so far, this is one of the typical example where we can use this smart inverter libraries, grid forming converter. In addition, we can use this library for rapid control prototyping and validation of islanded microgrid. We also can use them the interaction study. We have the choice over there for Droop control, VHG control, synchron water control. So if we have consider an islanded microgrid where different generation units are driven by different control algorithms, how this system interacts with each other. It is also one of the possible combination that in an islanded microgrid, some of the generation units are running as a grid forming converter. Some of the DG units can run as a grid following converter. So in that case, how these systems will interact. So these sort of studies we can conduct through these smart inverter libraries. In addition, we can study the frequency voltage stability analysis. The library also provide a flexible platform for validating in different topologies of the power system it is connected with. We also can use it for transient stability analysis, and most importantly, we can use it for the integration with grid following library to assess the compliance with different standards that is available as a safety functions or different programmable grid support functions available in the grid following library that was developed according to IEEE 1547 standard. So with the current version of the grid forming library, we actually need to further develop this grid forming libraries, and in future more functionalities will be added with it. It can be like we are about to integrate the secondary controller. We are about to integrate the virtual inertia or virtual impedance loops over there. With the current version of the smart inverter library, we do not have any islanded detection function, but that is available with the grid following library. So that functions we will integrate in futures. We also can integrate the different configurable protection functions in compliance with different grids and standards. So these are the stuffs that will be added in future releases of the smart inverter library.